This is the problem-solving portion of lecture 15. We're trying to find all possible non-isomorphic group types of groups of order up to and including 8. Now, in this problem-solving session, we'll go a bit beyond that. We'll look at groups of order 9, 10, and 11. And since we've already done the analysis, the same kind of thing for G4 and G6 and G8, the same kind of techniques we will use. And you can just look at the board, right? It's pretty dense, right? So it's the same kind of analysis that we did for those other 3 groups, G4, G6, G8, right? With a few new tricks thrown in. All right. Okay, well, let's start with the easiest one, just G11. 11 is a prime, so immediately we know there's only one type of group of that order. So it's a prime ordered group, right? Because 11 is prime. And therefore the only type of group that's isomorphic to G11 is the cyclic group, right, of order 11. So this G11, so order is 11, is isomorphic to the cyclic group order 11. Right? So that's done. Easy. Alright, now it gets tougher. So let's do G9. And remember the basic theory, the main tool that we're using in all this analysis is in fact a corollary, a quick derivation from the famous theorem of Lagrange, which says that the order of a subgroup divides the order of the group, or alternatively expressed, the order of a subgroup is a factor of the order of the group, of its parent group. Now, an alternative way to say much the same thing is to say that the order of any element of the group, the parent group, divides or is a factor of that parent group. And in fact, that's that corollary. That's the one we're using. So the order of any element of a group divides the order of the group. Okay. So in the case of G9, so the order of the group is 9. What factors are there? What possible orders can our elements take? Well, what are the factors of 9? Well, there's 1, there's 3, and there's 9. That's it. Now, forget about order 1. That's just the trivial group. We already know that. So what are the possible orders of the elements? Non-trivial, non-1, non-unit. Okay, so they have to be of either order 3 or order 9. That's a result of the corollary, right? Okay, well let's go top down. Let's go from the highest to the lowest. So let's start with the highest. So imagine one of those elements, at least one. There may be more. You can have. It's quite possible in a group to have several generators. Let's say there's one. So let A be an element that has order 9. Okay, the order of the element. So if that's the case, given the order of the group is 9, that makes this element a generator. Okay, and hence the group must be cyclic. Okay, now it's order 9, so it's cyclic. So here we have one type of group of order 9, it's cyclic. Now that will be true, and I've said this several times, but it doesn't matter what your order is. G of n, there will always be a cyclic group of order n. Yeah. All right. Okay. So we've found one at least. C9, the cyclic group of order 9. Okay. Now assume. So we've done that category. Now assume that there are no elements of order 9. and hence, except for the unit, all the rest, the other 8, must all be of order 3. Has to be, right? There's no other possibility because of the corollary. Okay, so they're all of order 3. Now, if let A be one of those elements of order 3. So we can generate a subgroup. That was one of the theorems quite a few lectures back from this element, E, A, and A squared. Remember that was the subgroup generated by an element, and it's a subgroup. So these 3 elements belong to this group, G9. These 3. Okay. So we've got 3 of the elements already of this group. Now let B be a 4th element. So B is by definition distinct from these. It's different. B is not that, not that, not that. Okay. So B is not one of these 3. So assume it's distinct. All right. Now assume also A and B are both generators. Let's just make that assumption. Now, the only way we can justify that is that they actually generate all the elements, and they're all distinct, right? So let's try to. So let's make it. So we'll try. We'll use A and B as generators to generate a 9-element set, right? So here we've got, here's your 4th element, B. Now if you have B, because it's a group, so you get closure, so B multiplied by any of these will give you BA squared, okay, so you get these. Now you can have BB in the group table, you know, B squared, so so we have to generate nine elements. So instead of being B squared being one of the others, let it be distinct, just on its own. I mean, it is its own element, B squared. And so if that's a member of the group, you know, you'll have B squared A squared, and so on. So here are 9. We've got so the A's, the B's, and the B squareds in a sense. So we've got 9 elements. Now, now that's a hypothesis. We suspect, you know, that's true. But to show we need to show they're all distinct. So we now need to prove that that's the case, that each of these 9 are different. Well, we can prove that by contradiction. So we assume the opposite. What's the opposite? That they're all different. Well, that there's at least one pair that are the same. So, you know, one of these and some other one of these 9 are equal. So in other words, in general form, we'll have something like this. So this is one of them, and this is another one. Now, the general form of this is A to some power, or well, you know, B to some power times A to some power. And these powers, I and J here, they can range over 0, 1, or 2. Okay? That's all the possibilities you have here. So I can be 0, 1, or 2, similarly for J. And assume this is you know, another one somewhere. So it will have the same form, but these numbers may be different. So K can range over 0, 1, or 2, and L also 0, 1, or 2. Right? So rewrite that as in this form. So you get the A's on the left-hand side and the B's on the right-hand side. Now, A and B both of order 3. Right? That's here. We've assumed that. Okay. So we can rewrite L minus J as P, and P will be what's the word? Congruent to this mod 3. Right? Because the order of A is 3. Right? And a similar story. Yeah. So similar story for Q, because B also has order 3. Right? So Q is congruent to I minus k mod 3. Okay? Now look, we assumed that when we introduced b in the first place, which was where? Here. We assumed it was a fourth element. So b is not b or a squared. Alright? Now the only way we can have b not being some power of a is, if you think about it, the only way we can have that and this be compatible because is if q is 0. It's the only way. That might not seem obvious to you at first, but think about it a bit. Okay, so the only way this and this are compatible is if q is 0, right? But if q is 0, then I minus k is 0 mod 3, or so we'll say I equals k. But if I equals k, that implies L is J. Why is that? Oh, okay. Because if Q is 0, B to the 0 is E, okay? And that means that P must be 0 as well. And if P is 0, L equals Q. Right. Okay, so I equals Q, L equals J. I equals, hold on, I equals K, so this equals that, and L equals J. L equals J. In other words, this and this are the same. So we assume, hold on. And we assumed, actually we assumed these two are different, and we had different integers here. We assumed they're different. Now we've proven that they're equal, right? So, that's the usual thing when you're trying to prove uniqueness, that there's only one way something can happen, is to assume that there are two ways and then show they're equal. So we assumed there were two different solutions, two of these that have the same value,